Alright, so I will be talking about couplings for stochastic differential equations with Levy noise. So I will focus on the following SDEs. So here we have just an SDE with additive noise, which is given by some pure jump Levy process in RD. So for this Levy process, I assume that the Levy measure is rotationally invariant, absolutely continuous. And I will impose some additional assumptions, but in order to keep at least the beginning rather simple, we can just think as a good example of this noise to be a symmetric alpha stable process for any parameter alpha between 0 and 2. But the results that I will be talking about work also for many other cases, even for some Levy processes with finite Levy measures. And also there are some possible extensions to the case where the noise is not necessarily only additive, it can be multiplicative, but you need to be able to somehow decompose it to have some additive component for this noise. And B is just a drift function which is supposed to be continuous and which is supposed to satisfy the following condition, which I call the one-sided Lipschitz condition. Sometimes it's also called a monotonicity condition in the literature. So this is obviously weaker than a classical Lipschitz condition. The interesting case is where a condition like this is satisfied with a negative constant on the right-hand side. So then we have an inequality which can be called a global dissipativity condition, which is quite a strong assumption for this kind of SDEs. If you have such an assumption, then you immediately get existence of a unique invariant measure for your SDE, and you get exponential speed of convergence in some Wasserstein distances. So I will talk about it in a minute. So an interesting question to ask is how can we relax this assumption to get still some related results, some ergodic properties for solutions to these SDEs. And I will show you here how to weaken these assumptions to something which I call dissipativity at infinity. So I still require this inequality to hold, but only if the distance between x and y is large enough. So a quick example, we will have a drift which is minus the gradient of some potential function u, then this global dissipativity condition somehow corresponds to uniform convexity of the potential u, and this dissipativity at infinity condition allows us to cover many other cases. So here in the picture you have the so-called double well potential, which appears in many applications. So generally speaking, as long as you have a drift which behaves nicely for large arguments, so in some sense for large arguments it pushes you towards the origin, then on some compact interval you can have quite irregular behavior. And I will be talking about things like speed of convergence of distributions of solutions to such equations to invariant measures. So I need some notion of a distance between probability measures. And here you can see the general definition of the LP Wasserstein distance. So if you have never seen it before, what happens here is that we fix two measures mu and nu on RD, and we compute an integral of some metric rho on RD with respect to a measure pi, which is supposed to be a coupling of mu and nu. So if mu and nu are measures on RD, then a coupling is a measure on R2D, which has mu and nu as its marginals. And then you need to consider infimum over all possible couplings. So this gives you a notion of a distance. And in this talk I will focus on the particular case where p is equal to 1, and this metric rho is given in terms of some concave function f, in the sense that rho is f of the Euclidean distance between x and y. So if f is concave, if it's 0 at 0 and strictly positive for strictly positive arguments, then we can easily check that rho defined in such a way is indeed a metric. And I will denote the Wasserstein distance associated with such a function f by wf. So this is still quite a general definition, which as special cases covers the total variation, in the sense that if we choose f to be equal to the indicator function of the strictly positive real numbers, then we get wf equal to 1/2 total variation. And if we take f to be equal to the identity function, then we get so-called standard L1 Wasserstein distance. So standard Wasserstein distances are the Wasserstein distances associated with just the Euclidean metric. Okay, and just a quick review of some known results for solutions to this kind of SDEs that I showed you. So here I work under such assumptions that the solution to my SDE is a Markov process. So it has some transition semigroup, which I denote by PT. And I use the following semigroup notation. If the initial distribution is mu, then for any t, the random variable xt has the distribution mu pt. And I'm interested in the speed of convergence of mu pt to the invariant measure. So as I already mentioned, if we have the global dissipativity assumption on the drift, then for any noise, we immediately get exponential contractivity of the semigroup in LP Wasserstein distances. So this exponential contractivity of the semigroup is just exactly this inequality, which you can see here. So from this existence of an invariant measure, of a unique invariant measure, immediately follows, and we get this speed of convergence to the invariant measure. So obviously, yeah, we want to somehow weaken this global dissipativity assumption. So there are many different results on this topic. For example, there is a very nice paper by Kulik from 2009, where under some kind of dissipativity at infinity condition on the drift, and also some technical conditions on the noise, he showed some convergence rates in the total variation distance. So he doesn't have contractivity in the total variation distance like here you have in Wasserstein distances, because usually something like this is impossible to show for the total variation, but you can still have exponential convergence rates in the total variation. There are some other results, like there's a paper by Priola, Shirikian, Xu, and Zabczyk from 2012, where they consider drifts which have some kind of a linear component and a nonlinear one. So then the nonlinear can be just bounded and Helder continuous, and as long as this linear one is a matrix with eigenvalues that satisfies some condition which in some sense corresponds to this global dissipativity condition for general functions, then they still get exponential convergence rates, but only in the case of symmetric alpha stable noise for alpha greater than 1. And for example, in Wasserstein distances, there is a recent result by G and 1, where again working under this dissipativity at infinity condition, and for noise which contains some symmetric alpha stable component, he showed exponential convergence rates in these WP distances. So here in this talk I will show you some method which allows us to get exponential convergence rates in both the total variation and the L1 Wasserstein distance at the same time under quite mild assumptions on the noise. So usually in most of these papers they have this either symmetric alpha stable noise or some non-degeneracy conditions on the noise. Usually what you need is you need quite a high small jump activity for your noise in order to get this kind of results. So here I will show you a method which works even in the case where you have a finite Levy measure for your Levy process. Okay, and the main tool which I will use is the coupling for a Markov process on RD. So we have seen this notion of the coupling of two probability measures in the definition of the Wasserstein distance. So here we have a coupling of a Markov process, or of two copies of the same Markov process, which is defined in the following way. So if we had a Markov process in RD, then a coupling is a process in R2D, which I here denote by x prime, x double prime. And it is called a coupling of xt if both these marginal processes have the same transition probabilities as xt. But they can have different initial distributions. Okay, so a good example of this is when we couple two Brownian motions by reflection. So if we have a Brownian motion started from some point x in space, we can choose a different point, it's called y, and then we can consider a Brownian motion which is reflected with respect to this hyperplane which is orthogonal to the vector x minus y, right? And what is important to mention here is that usually when we consider couplings, we are only interested in the behavior of the second marginal process until the first time when it meets with the path of the first process. So this time is called the coupling time, and usually we just require this second process to follow the path of the first process after coupling time. Okay, and so what is the connection between couplings of Markov processes and these Wasserstein distances? Well, whenever we have a coupling, so here I have some coupling xt and yt with initial conditions mu and mu, then it's quite easy to see that for any fixed time t, the joint law of xt and yt will be a coupling in the sense of couplings of measures of the laws of xt and yt. So obviously, when we compute an integral of some function f with respect to this joint law pi t, then in a trivial manner it gives us an upper bound on the infimum of these integrals over all such couplings. And the thing that appears on the left-hand side is exactly the definition of this wf distance that I showed you in the beginning. So again, any coupling gives us an upper bound for this wf distance. So of course, if we are interested in getting sharp estimates for these kind of distances, we would like to be able to construct couplings which are optimal. So an optimal coupling for this kind of problem would be a coupling which would actually realize this infimum. In practice, this is usually very difficult to obtain, but we can still hope to obtain some couplings which will be close to optimal in some sense. Okay, so coming back for a minute to the diffusion case, so I mean, we have seen this coupling by reflection for Brownian motions, but here we are interested in SDEs. So before I talk about SDEs with jump noise, let's take a look at SDEs driven by Brownian motion. And this idea with reflecting the Brownian motion can be somehow extended to this kind of SDEs with some nonlinear drift. So this traces back to a paper by Lindvall and Rogers from 1986. So what happens here is that they define a coupling by reflection for diffusions by defining the second marginal process in the coupling as a solution to an appropriately constructed SDE. So here we apply some kind of a reflection operator to the noise. So in principle it is a similar thing that you saw in this picture earlier, but here this hyperplane with respect to which you do the reflection changes continuously in time because of this additional drift that you have. And it turns out that for SDEs of this form, these couplings by reflection are very good for obtaining some bounds for Wasserstein distances. So here I have some results in the diffusion case, which are actually due to my PhD supervisor, Andreas Iberle. So he considered such equations under this dissipativity at infinity condition for the drift, and he showed exponential contractivity for the semigroup associated with the solution to this equation in some WF distance associated with some appropriately constructed function f. So the important thing is that you construct this function f in such a way that it is comparable with a rescaled identity, and then from this inequality you easily get some weak contractivity in the L1 Wasserstein distance. Yeah, so here is a picture which shows how this function f looks. So the important thing is that you construct some concave function and then you extend it in a linear way. So this somehow corresponds to the fact that you have a drift which for large distances behaves in a nice way. So because of this, for large arguments you can have just something like identity, and inside some compact set you really need to use this concavity in order to obtain your bounds. Yeah. So as I said, this allows you to get an inequality like this. And what is interesting that until recently, something like this was only known under global dissipativity assumption of the drift. And Andreas Iberle managed to use couplings and this method of constructing this artificial Wasserstein distances in order to get something like this under weaker assumptions on the drift. And I wanted to do something similar for the Levy case, but for this I needed to change, to come up with some good construction of a coupling. So the thing is that there's clear indication that some kind of a reflection works quite well for this Wasserstein distances based on concave functions, and so I wanted to first focus on some Levy processes which have rotational invariance in order to apply reflection once again. Because in principle, if you have a process with jumps, you can also define a coupling by reflection for an SDE with such a noise in a way which is analogous to what we have seen in the diffusion case. The problem is that if you just use such a coupling by reflection, it doesn't really work very well for obtaining good convergence rates. And intuitively speaking, the reason for this is that if we just start reflecting jumps of some process which has unbounded jumps, then it may happen that once your processes are already very close to each other, then you may suddenly have a big jump in the wrong direction, which can really spoil your convergence properties. So you need to have some alternative coupling construction which significantly reduces the probability of something like this happening. And the idea for how to construct such a coupling comes from the optimal transport theory. So so here very briefly we can take a look at two classical problems from optimal transport. Let's take a look at the second Kantorovich problem. So here we have some two measures, and we are interested in transporting the mass of the first measure onto the mass of the second measure. So this somehow corresponds to constructing a coupling of these two measures, which would somehow encode the way in which we transport this mass. And we want to find a coupling which would minimize the transport cost, which is defined as an integral of some cost function c with respect to this coupling gamma. And there is a paper by McCann from 1999 where he proved how you should do it in one-dimensional situation for concave cost functions. So he proved that there actually exists one coupling which is good for all concave costs. And this kind of concave cost functions somehow correspond to these Wasserstein distances associated with concave functions that we consider here. So how this coupling works? So let's imagine we have two measures, arbitrary measures on the line, and we want to somehow transport the mass of mu onto the mass of mu. So it turns out that what we should do is we should keep in place the common mass, and then we should apply to the remaining mass something which can be called anti-monotone rearrangement. So we essentially take, for example, the leftmost quantile of the first measure, and we map it onto the rightmost quantile of the second measure. And this gives you a coupling which minimizes the transport cost, concave cost functions. So of course, an interesting question is now how to somehow translate this into the language of coupling to solutions of these Levy-driven SDEs. So yeah, I mean, in this case we are actually interested in coupling two copies of the same Markov process. So in such a case, this coupling by anti-monotone rearrangement can be thought of as just a coupling by reflection. But I think that before we move on to the Levy processes, it's also instructive to take a look at the construction which is presented in a paper by Xu and Sturm in 2013. So they define something which they call a mirror coupling. And their paper is mostly about Brownian motions, but their construction is general in the sense that you can apply it to any Markov process. So they somehow explain this construction on the example of coupling two copies of some density in one dimension. So we can imagine that we have some family of transition densities, P of x, and we just choose 2 points in R, and we consider 2 copies of the same density, but fixed at 2 different points. And yeah, so Xu and Sturm also point out that there exists this mirror coupling, which is then a measure on R2, which minimizes the transport cost for concave cost functions phi. And the way they present this construction is that they show how to couple 2 random variables. So the idea is that we have a random variable zeta1, which has the density p of x1, and then we want to construct a coupling by defining a new random variable zeta2, which will have the density p of x2, so that we actually have a coupling. But this coupling needs to be constructed in such a way that we really get this minimal coupling, or the optimal coupling M. So it turns out that, so if you have this first random variable, which just takes some value in R according to its density, then you should construct the second random variable by allowing it to only take 2 possible values. So here I have these formulas. So if zeta1 takes value z1, you should either assign the same value to zeta2, or you should assign a value which is reflected with respect to, a hyperplane orthogonal to x1 minus x2. So of course in one dimension we just reflect with respect to this point in the middle. But here I have a picture which presents a particular case when we take density with bounded support. So here in this picture we can take a look at how these formulas really work. So what can happen here? If we assign a value z1 to zeta1, which is outside of the support of this second density, then obviously this quantity is 0, and then this fraction here is 0. So then with probability 1 we reflect the value of the second random variable. If z1 is somewhere here, then we actually have a value for this fraction which is strictly between 0 and 1, so then both cases are possible. And it may also happen that z1 is somewhere here, where the value of this will actually equal to 1. And then with probability 1, we assign the same value to zeta2. So here is a formula for this coupling M. So if you just write down formally what we saw in the previous picture, this looks, yeah, this is how it looks. And then if you want to formally prove that this is a coupling, then you really need to use the fact that you have symmetric transition densities. So this construction works for the symmetric case. So this, I hope, somehow indicates what you should do if you want to couple 2 processes with jumps. So this would mean that if you have 2 processes which jump from 2 different points in space, then you should either keep reflecting the jump of the second process, or you should force these 2 processes to jump to the same point. So I will show you now how to do this formally in the case of Levy-driven SDEs. So I have some noise in my SDE, which I denote by LT. And of course we know that by the Levy decomposition we can just represent it as integrals with respect to some quasi-random measure n. And we also know that a Poisson-random measure can be represented as a sum of Dirac masses at some points. Let's call them tau j, psi j. So these points, in some sense, encode the times of jumps and the sizes of jumps. And so this is a Poisson-random measure on R plus times Rd. And we do the following trick for technical reasons. So we embed this n in R plus times Rd times 0, 1. So we essentially add here some additional random variables eta j, which are uniformly distributed on 0, 1. And we rewrite Lt as a sum of two integrals with respect to this new Poisson-random measure n. So this is just, so this doesn't change the behavior of Lt in any way. We do it to get some additional variable which we will use as a control variable for our coupling. So here we have Lt which behaves in exactly the same way, but now with every jump we additionally draw this random number which is uniformly distributed on 0, 1. And now, as I said, so we have a process which jumps, let's say, at time t. So xt makes some jump of size d. And then we should decide what to do with this second marginal process in our coupling. So we should either reflect the jump or we should force y to jump to the same place where x jumps to. And of course, in order to obtain a coupling, we need to somehow correctly specify the probabilities of these two events happening. So we will define some control function, rho, with values depending on this size of jump of our first process and on the distance between our two processes before the jump. And with each jump we will compare the values of this control number u with the values of this control function rho. And depending on the outcome of the comparison, we will either do the reflection or we will force the processes to meet at the same point. So how do we define this control function? Well, here I work under an assumption that my Levy measure is absolutely continuous, so it has some density which I denote by Q, and what we really need to do is we need to couple two copies of this density. So we have a density which somehow corresponds to the position of the process X before the jump, and we have a translated copy which corresponds to the position of the second process. And we just couple these two copies in the same way as we coupled these two densities in this construction that I showed you that came from this paper by Su and Stuhl. So this is the formula for rho that we get, and knowing all this, we can actually try now to formally define the coupling that we want to use. So recall that this is the SDE that we have, so we can rewrite it in terms of this driving Poisson-random measure. So here I just wrote it as if we compensate over whole RD for brevity. So this doesn't have to be the case, but I want to have formulas that fit into the screen. Because this is how we define the second SDE. So, yeah, here of course we don't really do anything with the drift. And here we have these two integrals which somehow correspond to these two choices that we have for the jump of our second marginal process in the coupling. So we have this integral which corresponds to the reflection. So here we use a reflection operator which is exactly the same thing that appears in this classical coupling for diffusions by Lindvall and Rogers. And here we have an integral which somehow corresponds to this possibility that we force yt to go to the same place where xt goes. So, yeah, everything that I have shown you up to this point is essentially some intuition on how to come up with this formula, but of course if we write down something like this, then we need to do all the technical work. So we need to prove that this system of two equations actually has a solution, and the solution is indeed a coupling. So this is something that has to be done. I don't really want to spend time here on the technical details. The fact that it has a solution can be shown using the interlacing technique, actually, because it turns out that you can write this second equation as an equation which has local Lipschitz coefficients plus an integral with respect to a random measure which has finite intensity. So then you can just add these jumps to your second process. And the fact that it is a coupling, well, intuitively the argument is related to this mirror coupling construction that I showed you, but of course in the case of Levy-driven SDEs it takes some space to write it down. But if we actually do the work and we have a well-defined coupling, XTYT, then we can actually write down this expression that we were interested in for the bounds for the Wasserstein distances, and we use the Ito formula, and then we try to somehow choose the function f in such a way that an inequality of this form holds, and then from the ground wall inequality we just get exponential convergence rates and exponential bounds for WF. So what is interesting here is that in the Levy case, the function f that we use here can be discontinuous. So if you remember, I showed you some results from the diffusion case where this function f was constructed in such a way that it was a concave function extended in a linear way. So here we have a function which has two components. So the second component is exactly something like this, but we also add something which corresponds to rescaled total variation. So this is how this new function looks here. So this has both advantages and disadvantages. So an advantage is that this allows you to compare your distance from below with both the total variation and the standard L1 Wasserstein. So you get exponential convergence rates in both these distances at the same time, but you don't get L1 Wasserstein on the right-hand side, which is something that can also be useful. So to get this weak contractivity for your same group in L1 Wasserstein, one application of something like this is that it allows you to obtain so-called transportation inequalities. So I will talk about it briefly at the end of this talk. But yeah, in this case, with a discontinuous function f, you get a bounce of this form. So let's take a look once again at the assumptions. As I mentioned, we need to have rotationally invariant Levy measure and absolutely continuous. So this is important for the construction of a coupling. And for our estimates, we also need some very mild assumptions on the concentration of the Levy measure around 0. So here we have some expression which involves density. So what happens here is that you consider is it chalk somewhere?
It's the box.
Here, okay. So you just have some density and you have a translated density, and you want this overlap to have a positive mass. So this is an assumption which is easily satisfied by many natural examples. You also want to have a condition like this, which essentially means that you need to have some mass around 0, but in combination these two assumptions allow you to consider even some cases of measures which don't have any mass immediately near 0. So it allows you to consider, for example, finite Levy measures of this form. So on our needs to be symmetric, but as long as this gap in the support near 0 is not too large, with this coupling you can still get a successful coupling for SDEs driven by such a noise, and you can get this exponential convergence. And under this set of assumptions, we get these bounds. So these assumptions allow us to work with this discontinuous distance functions. What is interesting is that if we replace assumption 3 and 4 with the following assumption 5, which is stronger, then we can get something similar to what we got in the diffusion case. So let's take a look at this assumption. Here I consider a first marginal of the measure mu. So of course mu is rotationally invariant, so I can just take any marginal. And I consider an integral of the square. So obviously this is final and this converges to 0 with epsilon. And this is an assumption which says that this should converge to 0 not faster than epsilon. So intuitively this means that you need to have enough mass near 0. So this is something that for which you really need to have infinite mass of your Levy measure. And but this is not sufficient. So for example, when we consider alpha stable processes, this is satisfied only if alpha is at least 1. So you really need to have noise with jumps, but with so many small jumps that it behaves more like a diffusion. And then you actually get this kind of results which you also get in the diffusion case. So this is quite interesting. While these estimates can be obtained under much milder assumptions.
Is that because your f is continuous?
Yes, so with this assumption I can use continuous f, and then I get these bounds, exactly like you get for the diffusions. Okay, so for the end of the talk I would like to actually show you why obtaining something like this can be useful. So I will talk a little bit about the transportation inequalities. Okay, I guess at first I have some possible extensions, because everything I talked about was only under the assumption that I have additive pure jump noise, but you can combine this with Gaussian noise, and you can also consider some multiplicative components in the noise. So here it's written in a bit of a weird way, so I have two Brownian motions and I have two jump noises. The important thing is that at this point I know how to deal with a situation where I have at least one additive component. Because when I have an additive component I can use either these methods from the paper by Andreas Igerle for the diffusion, or from my paper with the jump noise. So then if I somehow include these multiplicative noises in my dissipativity condition, then I am still fine. So this essentially means that you have a drift which is strong enough at infinity that it somehow counteracts this additional perturbation that comes from the multiplicative noise. But for the coupling itself, all the work is done by some additive component. Yeah, and then, as I said, I can somehow combine this reflection coupling from Limval and Rogers and the coupling for the pure jump case and still get an inequality like this. Okay, so very briefly I will tell you something about these transportation inequalities, which are related to the contractivity of the semigroup in the L1 Wasserstein. So what are those transportation inequalities? So these are somehow inequalities which relate the notion of this L1 Wasserstein distance to the so-called relative entropy or Kullback-Leibler information of one measure with respect to another. So if we have some deviation function alpha, which is supposed to be non-decreasing left continuous starting from 0, then we can have this kind of alpha W1H inequality. So it as I said, it relates standard L1 Wasserstein distance with this relative entropy H. So this looks quite abstract, but there is some nice characterization of these inequalities. So in the third point, for example, we can somehow interpret this transportation inequality as something that gives us explicit bounds on the error of Monte Carlo integration of some function. Because here we just draw some sequence of IID random variables with some common law mu, and we just consider some Lipschitz function, and so this is like Monte Carlo integral of f with respect to mu, and here mu of f is just an integral, a real integral of f with respect to mu, and this gives you some explicit exponential bounds in terms of this deviation function alpha, and this is equivalent to this alpha W1H inequality. Yeah, and it turns out that in some sense you can obtain this inequality. So in some sense, this property characterizes concentration of your measure. Does alpha? Okay.
So, is it a deviation function or the deviation function?
No, it is exactly the deviation function that appears in the inequality. So if mu satisfies this inequality with some specific deviation function alpha, then this is exactly the deviation function alpha which appears in this bound.
Yeah, but in principle, is it dependent on the law of these random variables?
Yes, I guess so. Yeah, sure. Yeah, because this is. Yeah, well, the deviation function you get depends on what probability measure you consider. So I actually consider this kind of inequalities for measures which are distributions of solutions to these Levy-driven SDEs. So yeah, here we could consider something actually with multiplicative noise. And so I probably want to skip some technical details. So under some assumptions on these coefficients, it is possible to show this kind of alpha W1H inequality with some deviation function alpha t for measures which are here denoted by delta x pt. So this is just pt is just a semigroup associated with a solution to some jump diffusion, and using the semigroup notation, if we start from the point x, then the distribution of a solution at time capital T is just this. And there are some results by Li-Ming Wu and by Yutao Ma which show such inequalities for solutions to these equations, but only under global dissipativity assumption of the coefficients. So global dissipativity in this multiplicative case should be understood in this more general sense, where you include these coefficients in your condition. And it turns out that using couplings, you can actually extend these results to the case where this dissipativity holds only at infinity, in the sense that I explained earlier. And for this, you actually need to use the Malyavan calculus. It turns out that these inequalities are somehow related to bounds on the Malyavan gradients of solutions to such equations. So here, this is a definition of the classical Malyavan derivative with respect to Brownian motion, but there are also Malyavan derivatives with respect to Poisson-random measures. So you can just consider difference operators, right? So if you have a Poisson-random measure, which is a sum of some Dirac masses, you can consider a modification where you add some additional mass at some point to and you can consider a difference operator defined like this. So again, skipping the technical details because there isn't time, but using the Clark-O'Connor formula, you can represent solutions to these equations in terms of integrals of these Malyavan derivatives, and then if you get some appropriate upper bounds for conditional expectations of these Malyavan derivatives, then it allows you to obtain some convex concentration inequalities for this kind of processes or random variables, and this in turn leads to the transportation inequalities. Yeah, and so what I did was I used couplings in order to somehow obtain appropriate bounds for the Malyavan derivatives, because in his original papers by Li-Ming Wu and Yutao Ma, these bounds were obtained under the global dissipativity condition only. And by applying couplings, it was possible to somehow extend this to these more general assumptions. Okay, I guess I will just finish here now. So just a few references. So yeah, this is the classical paper by Lindvall and Rogers for coupling by reflection from diffusions, and the paper by Andreas Iberle, where he got this exponential convergence for diffusions using this coupling in Wasserstein distances. I did something related for this pure jump Levy case first, and then I applied this to transportation inequalities. And this is again the original paper on transportation inequalities by Levy. This is actually quite nicely written. So if you are interested in this kind of things, I would definitely recommend this particular reference. Okay, thank you very much for your attention.